Okay, so I'm gonna show the program running on each of the 17 trace files, and I'm gonna do it by running this shell script, which will allow me to show the outputs of each of the tests in two separate files so that you can compare the output of the TSH that we coded and the reference TSH. Okay, so I'm gonna be walking through every function except for eval. So for built-in command, all we have here is that it looks at the first value in the argv array. If it's null, then it just returns. If it's quit, then it exits the shell. If it's jobs, then it lists all the jobs. And if it's bg or fg, then it runs the do bgfg function. Now for the do bgfg function, at first we just have a bunch of validation. So if the required second argument wasn't provided, it just returns and prints an error message, right? It checks to see whether the JID or the PID was provided. It checks to see whether the number actually provided, whether the argument provided is actually a number. And then it gets the corresponding job from the PID or JID and checks to see whether that job slash process actually exists. Now here we use kill to send a sigcon signal to the entire process group. This is so that any stop signal gets continued. And then if the command called was fg, we switch the state to fg and we call the blocking wait fg function. If it's bg, then we switch the state correspondingly and we print the background information. Now for wait fg, here we simply create a sig set that is empty, and we simply enter this while loop and we call it sig suspend in order to freeze this process. Now when we get a signal, we check if The FGPID is still this process, and if it's not, then we return. If it is, then we keep going and wait for the next signal. So here we've got the SIGCHILD handler. What this does is that we call wait PID with -1, meaning it waits for any child of the calling process, and we use this WNO hang and WUN traced so that wait PID returns whenever the child is still running or whether it's stopped. Now, if it's stopped, which is what we check for here, then we print that it was stopped and we give the number of the signal and we simply change its state and we continue with the next iteration. Now, if this was terminated by a signal, then we print that out. We print that out and we delete the job. Now for the SIGINT handler, we simply get we simply get the ID of the process running in the foreground and we send a SIGINT signal to the entire process group, which has the effect of stopping it, or terminating rather. And then for our SIGSTOP handler, we do a very similar thing. We get the FGID and we send a SIGSTOP signal to the entire process group in order to stop those processes.
One of the main subroutines of the code base is the eval function, which takes in a string representing the command line. Right off the bat, the command line gets parsed into an argv array, doing an early return for blank lines or if it successfully ran a built-in command. From this point, the command line string is parsed into a custom structure which concisely holds relevant information that helps with dealing with file redirection and pipelining. CMD line holds a background flag and a list of argv structs representing each subprocess in a chain connected by pipes. Each argv struct contains the actual argv array and any in-out files from input-output redirection. And here's the initializer function which parses the command line. Back to the code. Next is blocking and ignoring signals to prevent bugs with unfortunately timed signals which may occur. From there, the process is forked. The parent makes sure that the child is in a separate group and adds a job to the job list before restoring the signal handlers. Depending on whether the command is running in the background or not, either prints a message or waits until completion. Within a child, the group is changed, the signal handlers are restored, and standard input-output is redirected. Redirect stdio function checks for any redirection for the current argv struct and replaces it with the relevant file descriptors. In the case that there are pipes, the doPipe subroutine executes instead of executing a single command. The main idea behind the subroutine is that it daisy chains each subprocess together using pipes. For example, take this line. When a child is forked for the ls command, the last in file descriptor is set as the input for ls and its output is set to the read end of the pipe. Redirect stdio is also called to handle file redirection, so in this case, it replaces the input with foo.txt. Meanwhile, the parent updates the last in file descriptor with the read end of the pipe, so that the next iteration of the loop, the output of ls gets sent to head. This repeats for all subprocesses except for the last one, as we do not want to take the output of tail to a pipe. This allows behavior that is identical to pipelines in bash. And that is it for the eval function.
Okay, so I'm gonna go through the 5 additional test cases that we added. So the first one simply tests piping. We test it on different lengths so that we're sure that it works on any arbitrary length. And here's the contents of the pipe file. Now if I run make test, we see that it gives a correct output. Now for 19, we simply test piping in conjunction with redirection. So we have an out file and an out file 2 here. And running the test gives us the correct outputs in each of the out files, as well as the correct output in this shell down here. Now trace 20 builds on trace 17 in that it tests redirection, but it tests both input and output redirection at the same time. You see that out file has the correct value. Now, for 21, we simply test that signals, namely sleep, namely int and tstop, actually work properly on piped commands. We see that we get a correct output here. Now, finally, for Tways 22, we check that the background operator and the FG built-in command works properly on piped commands. And we see that it gives a good output.
Issues encountered. There were a handful of issues that were encountered during this project. One of them arose when implementing pipelines, since they made interpreting the argv array much more complicated. This was remedied by creating an argv and CMD line structures, which better grouped relevant informations together in an easy to work with fashion. This made implementing pipelines much easier compared to having to deal with a bunch of random strings. Another one was the actual implementation of pipelines, which took unexpectedly longer than anticipated. To complete this, we took a step back and going back and forth on the core ideas behind pipelining and discussing how those ideas can be translated into code. Eventually, we did manage to simplify the task into something manageable and implemented. And the final difficulty was finding time to do pair programming, as our schedules differ and we might not always be available at the same time, at the same place, on certain days. Doing this was solved by doing pair programming over a video call, as it allowed more flexibility in our schedule to complete the task.
So as for my contributions, the paradigm we used was a peer programming one. So with me as driver and Raymond as navigator, I coded a built-in command, do bgfg, wait fg, and the sigchild handler.
Where I was the driver for implementing the eval function, sigint, and sigstop handlers, with Zane as my navigator.